Good day to you. In this episode, we're going to explore some of the behaviors of gases. The theory of gases was one of the foundations of the science of thermodynamics. It was in gases that, for the first time, clear connections could be drawn between the simple behavior of atoms, governed by nothing but Newton's laws, and important thermodynamic concepts like energy, work, and entropy. The people who made these connections, people whose names you'll recognize like Robert Boyle, Daniel Bernoulli, Ludwig Boltzmann, and James Clerk Maxwell, did so using highly mathematical arguments. And you had to be adept at mathematics yourself if you're going to understand the theory. Fortunately for us, we have digital computers and software tools to simulate these things, so that even if we are not mathematically adept ourselves, we can still visualize the behavior. And we're going to use one of those tools today, a program called NETLogo. NETLogo was developed by a programmer, Yuri Velinsky, originally at MIT, then at Tufts University, and now he's at the Center for Connected Learning and Computer-Based Modeling at Northwestern University. NETLogo is a so-called parallel agent-based simulation environment in which agents, called turtles, can move about a space with their behaviors governed by the properties of the space they occupy and by rules of interaction with other agents. It's a fun program, and best of all, it's free and downloadable from the NETLogo site. Here's the URL. You can also find it just by Googling NETLogo. Included in the package is an extensive model library, some of which we'll be using here today. And you can program it yourself. I've used it myself to simulate termite behaviors. Try it yourself. It's a really fun program. In the simulations we'll use today, the turtles are treated as gas molecules that can move around an arena, bounce off walls and each other, and so forth. Pretty simple stuff, but that's the point. Thermodynamics is a complex science that arises out of simple rules. Okay, with that, let's get started with the fun stuff. We're going to start with a basic NETLogo simulation known as GasLab Free Gas. You can find it by going to File and then to the Models library. Here's the screen view. Let's orient ourselves. The central part is an arena where particles of gas can fly around. They can collide with the walls and bounce off them, and you can also set the simulation so the particles collide and bounce off one another, or not. There are several panels for setting up the simulation. You can set the number of particles, their initial speed, roughly proportional to the temperature, and how heavy the particles are. You can also set the simulation to trace the path of a particular gas particle. There are several panels that report out important measures from the simulation, including the particle's average speed, their average kinetic energy, which is 1/2 mass times the velocity squared. It also reports out how many particles fall into one of 3 speed classes: fast, medium, and slow. In addition, the simulation reports out the speed classes with respect to time and shows rolling distributions of both speed and kinetic energy. Finally, notice how the particles in the arena are colored blue, green, and red. This tells you which speed class each particle falls into. Okay, let's get started. First, let's see how collisions between molecules affect the distribution of kinetic energy in the gas. Let's first set up the simulation. We'll set the number of molecules to 200, and we'll leave their mass at 1. We'll begin with a moderate initial temperature, which gives us an initial speed of 10. We're going to turn tracking off for the moment, and we'll turn collisions off as well. Finally, we're going to slow things down a little bit so we can more easily see what's going on. Now we press Setup, and we're ready to go now. The main thing to notice here is that the speeds and the energies of the gas particles are steady at what we set them to be initially. Let's speed things up and turn tracking on so we can see more easily what's going on. As you can see, the velocity of the molecule never changes. Okay, that's pretty boring. Let's stop that and set it up again. We'll turn tracking off and we'll begin now. We see the same thing as we saw before, but now watch what happens when I switch collisions on. Look how the distribution of speed and energy immediately spread. What is happening here is that collisions can now alter a molecule's velocity. Depending upon the angle of the collisions, gas particles can be made to speed up or slow down. Let's turn tracking on to see how this works and speed things up along a little bit. Note now how the color of the trace changes. This is reflective of the change of velocity of the molecules. Sometimes the collisions speed them up, sometimes the collisions slow them down. Okay, let's turn now to see what happens when we allow molecules to collide with a wall. We'll first look at the effective number of particles. For this, we're going to use a model known as Gas Lab Pressure Box. It's found under the curricular models in the models library. Gas Lab Pressure Box has many of the same features as free gas, except molecules can now impart momentum to a wall, outlined here in yellow. We can also add particles to the chamber through a nozzle located here, and we can add them in puffs of any number of particles. We can add them in puffs of 1, for example. There it went. We can add them in puffs of, say, 21. For our purposes, we're going to add them in puffs of 50, like so. Okay, let's stop this, set it up again, speed things up so we can get data more quickly, and we'll let it rip. Now, it looks like with 100 particles, the pressure is averaging out to around 47.9. Let's make a note of that. Let's now double the number of particles from 100 up to 200. That's 2 puffs of 50. Speed things up so we can get some data quickly. And it's looking like that's going to average out to around 97 or so. Let's make a note of that number as well. Let's slow things down a bit. Let's double the number of particles again, up to 400. Okay, let's speed it up so we can get our data. And it's looking that's going to average out to around 194. All right, let's slow things down. Double the number of particles again, up to 800. There we are. Speed things up so we can get some data. With 800 particles, it's looking like it's going to average out to around 391. Let's write that number down. And let's just double the number of particles once more up to 1600. That's going to be 16 puffs of 50. There we are, 1600. Speed things up so we can get our data quickly. A little faster. And it's looking like that's going to average out to around 792. Okay, so we'll make a note of that as well. All right, we have the data in hand. Let's now go to Excel to see what it looks like. Okay, here are the numbers. Particle number is here, and pressure is over here. Let's do a simple plot. We'll highlight them both. We'll insert a scatter chart, like so, and there are the numbers. It looks pretty linear. Let's confirm this by adding a trend line. Let's choose a linear model. Let's display the equation and a measure of goodness of fit on the chart, and here we are. It looks pretty good. Slope of 0.4961 and an R-squared value, which is essentially a measure of goodness of fit, very close to 1. This means it's an almost perfect linear fit. Thus, pressure is directly proportional to the number of particles. This makes sense. Pressure is proportional to the momentum imparted to the walls. The more particles, the more collisions there are, and the more momentum is imparted, and the higher will be the pressure. Okay, what happens if we change the size of the box? For that, we go to another NETLogo model. To simulate the effect of volume, we'll use a model known as Gas Lab Isothermal Piston. Isothermal just means the temperature has been clamped at some value. This is to avoid a complication that arises in real gases, namely that they heat up when compressed and cool down when they expand. Isothermal piston also has many of the standard gas lab features, but we can now change the volume of the box by moving one wall, here in orange, to the left or to the right, as if the wall was a piston. Okay, let's get started. We've set the number of particles to 500. The piston position is at 0. Let's compress the gas a bit, down to about a third of its original volume. And go. Now the volume is about 360, and the pressure looks to be averaging out at about 3,810. Let's make a note of that. Let's now allow the gas to expand a little bit, by about that much, and go again. Now the volume is 880, and the pressure looks to be averaging out at about 1,470. Let's do that again, and go. Pressure goes down again. Our volume is about now 1,520, and the pressure looks to be averaging out at about 720. Let's let it expand again to about this much, and go. Now the volume looks to be about 2,280, and the pressure looks to be averaging at about 530. And once more, almost to the entire volume, and we'll go again. Now our volume has gone up to 3,000. We'll just make a note of that. And the pressure has declined now to about 380. Okay, we have those data in hand. Let's now go to Excel to see what it looks like. Okay, here are the numbers we've gathered. Volume over here, and pressure over here. Let's turn those into a scatter plot. So, pressure obviously goes down with volume, but it doesn't go down in a straightforward way. But let's try a little trick. Let's calculate the inverse of the pressure. Let's put in our formula. Put in a formula here that actually calculates the inverse. Copy that formula into the other cells. And let's see what happens when we plot that versus volume. Voila, it's linear. Let's put in a trend line just to make sure. Do a linear model, display the equation and the r² value on the chart, and sure enough, it is linear. In short, pressure varies with the inverse of the volume. So both particle number and volume affect pressure, but in different ways. Can we put these together somehow? We can use isothermal piston for a kind of experiment to show how it can be done. What we can do is see how pressure is affected by different combinations of volume and particle number. For example, we can set a particle number, say 100, and see how pressure is affected by different volumes, 600, 880, 1200, 1800, and 2400. We can then set particle size to 500 and go through the same range of volumes, 600, 880, 1200, 1800, and 2400. There's no need to go through them all here. Let's just go straight to the data. Okay, here are the data all keyed in. I simulated pressure with 5 different numbers of particles, 100, 250, 500, 750, and 1000, and at 5 different volumes, 600, 880, 1200, 1800, and 2400. Next to the data is a 3D plot showing how volume and particle number together affect pressure on the vertical axis. This is still too complicated though. So let's use our trick again. Here I've taken particle number and volume and calculated from them the particle density, N over V. And when we plot pressure against those, we see a linear relationship. This says something very important about gas pressure. It is proportional to particle density. You'd think it might be proportional to the surface area of the box because pressure comes from particles colliding with a wall. The more wall, you'd think there'd be more pressure, but that would be wrong. It's particle density, no matter how capacious the wall is. Real gases are often mixtures of different gases. Our atmosphere, for example, is a mixture of nitrogen, oxygen, and small amounts of CO2, water vapor, and other trace gases. Living things in particular depend upon how these gases mix. We can use another gas lab simulation, 2-gas, to study this. We've changed the one you see here a little from the one that you see in the model's library. 2-gas divides the world into two compartments, left and right, that are separated by a wall, within which there is a port that can be either opened or closed. Here the two gases have the same mass, but different initial speeds. This corresponds to one being cooler than the other. Now let's watch what happens when we open the port. As the slow particles, the magenta ones on the left, collide with the fast molecules, the cyan ones on the right, there is a net transfer of momentum, so that the average speeds and energies of the two types of molecules equalize. We'll come back to this in more detail in another video. What really interests us here is how the two gases mix. The most basic mixing process is a process called diffusion. We can use 2-gas to look at this in some detail. We're going to follow how quickly either type of molecule moves to the other side, that is, how fast the magenta particles move from left to right, and how fast the cyan molecules move from right to left. These numbers are plotted on this top graph over here. We'll start with equal numbers of molecules with the same size and same initial speeds. This corresponds to pressure and temperature being equal on either side of the barrier. So let's open the wall all the way and let her rip. Look how even the mixing is. That is, the magentas move from left to right as fast as the cyans move from right to left. Now let's complicate things a bit. What happens if one molecule is larger than the other? That's easily done. We have to set things up so that the energies on either side of the wall are equal, but I've worked out that these numbers for mass and initial speed work well. Okay, so let's open the port and see what happens. Notice how the mixing is asymmetrical at first. Specifically, the lighter magenta molecules mix faster than the heavy cyan molecules do, even though they have the same energy. This is an important feature of diffusion mixing. The heavier a molecule is, the slower it diffuses. Okay, one more simulation to go. Pressure only arises if there is something for gas molecules to collide with. That is why, for there to be a pressure, the gas must be confined in a container. But what if there is no container? Our atmosphere is like that. It's not confined to anything. So why is there such a thing as an atmospheric pressure? We can see why using a simulation called Gas Lab Atmosphere. Again, we've modified it slightly from the one you can find in the model's library. The answer in a word is gravity. It's hard to imagine, but even tiny gas molecules have mass, and that means that gravity will accelerate them toward the Earth. Let's trace some molecules. You see the typical parabolic trajectory of a molecule colliding with the surface, then bouncing up, only to be drawn back down by gravity. Note that we're not allowing collisions between molecules here. Let's boost the number of particles and switch collisions on now. We see two very interesting things. First, the action of gravity makes for a high particle density close to the surface. Any object there will therefore experience a high atmospheric pressure. Gas density declines with altitude, however, and this is why atmospheric pressure declines with altitude. Second, we see that gas particles occasionally get enough momentum to reach escape velocity. This means that the atmosphere is continually losing gas particles to space. You can see how fast the particles are lost on this graph here. This is for a gravity equivalent to Earth's, 9.8 meters per second squared. There is not a lot of loss. Nevertheless, a stable atmosphere has to replace those molecules somehow. For Earth, this comes from outgassing from the core and capture of solar wind. Now let's see what happens when we reduce gravity. We're going to set gravity to about 1/6 that on Earth. That's roughly equivalent to what it is on Mars. The increased loss of gas from the atmosphere is dramatic. This is why a small planet like Mars has a thin atmosphere. We can eliminate the loss of gas by restoring gravitational attraction close to what it is on Earth. Okay, that was fun. Let's review what we've learned. First, we saw how random collisions between molecules produce a statistical distribution of speeds and hence kinetic energies. This has important implications for what kinds of things gases can do. If a chemical reaction, for example, requires a gas molecule to have a particular energy, only a certain proportion of molecules in a gas will have enough. This proportion can be worked out quite precisely. When you take chemistry, pay attention. They'll tell you how to do it there. Second, we saw that the large-scale phenomenon of gas pressure emerges from innumerable transfers of momentum to a solid object, such as a wall, each transfer resulting from the collision of a gas molecule with a wall. Again, this can be worked out mathematically, but fortunately, someone's done it for us already. This is the ideal gas law, which you should brand into your brains, PV equals nRT. Here, the surprising result is that pressure is a function of particle density, how many molecules are confined in a given volume. Despite pressure resulting from an interaction of gas molecules with a surface, pressure is not proportional to the container's surface area, only to the density of the molecules. Third, we saw how particle size affects the consequences of momentum transfer between molecules, specifically how the speeds of large molecules are only slightly affected by collisions with small molecules. This is important for the phenomenon of diffusion. And finally, we saw that the phenomenon of atmospheric pressure results from gravity biasing collisions of gas molecules with the Earth's surface and every surface there, including ourselves. This tells us not only why atmospheric pressure exists in the first place, despite the atmosphere being an open system, but it also tells us something about atmospheric dynamics. Well, that's all for now. In another episode, we'll be connecting these simple behaviors with thermodynamics and concepts like work, power, and entropy. Until then, this is Scott Turner, wishing you a good day.